We'll start in 1 minute. We'll continue the test 2 review today. Test 2 is on Friday. Tomorrow I will email the Zoom link for the test on Friday. So we did one example of a hydrostatic force. So for now, let's skip past number 6. And if there's time, we'll come back to do number 6 later. Let's do number 7 on finding the centroid of a region. So for this one, find the centroid of the region bounded by the graph of y equals x to the third, y equals 0, and x equals 2. So y equals 0 is the x-axis. Remember the formula for the moment of the region about the x-axis, m sub y is equal to rho, which is the density factor. We're assuming uniform density multiplied by the definite integral from a to b of x times f of x dx. And the moment of the region about the x-axis, m sub x is equal to rho times the definite integral of from a to b of 1/2 times the square of f of x. And then the mass of the region is just rho times the area, so that's rho times the definite integral of f of x dx from a to b. Okay, so for this one, our function f of x is equal to x to the third, and we're going to integrate from x equals 0 to x equals 2. So the moment of the region about the y-axis is rho times the definite integral from 0 to 2 of x times x to the third dx. Okay, so this is a simple integral to evaluate. We'll simplify the integrand to x to the fourth. And then it's rho times x to the fifth over 5 evaluated from 0 to 2. And so 2 to the fifth is 32, so we get 32 fifths times rho. Hey, the moment of the region about the x-axis, this one is rho times the definite integral from 0 to 2 of 1/2 times the square of x to the third. So this is rho times the definite integral from 0 to 2 of 1/2 times x to the sixth dx. So we get rho times 1/2 times x to the seventh over 7 from 0 to 2. And 2 to the seventh is 128. So 1/2 of 128 is 64. So we get rho times 64 over 7. Or if you want to write it as 64 sevenths times rho. And then finally the mass is rho times the definite integral from 0 to 2 of the function x to the third dx. So we get rho times 1/4 times x to the fourth from 0 to 2. 2 to the fourth is 16. 1/4 of 16 is 4. So this simplifies to 4 times rho. The x coordinate of the centroid, x bar, by definition, that's m sub y divided by m. So m sub y is 32 fifths times rho, and then we're dividing by the mass 4 times rho. The rho's cancel, and 32 fifths divided by 4 is 8 fifths, or 1.6. The y-coordinate of the centroid, by definition, is m sub x divided by m. So this one is 64 sevenths times rho divided by 4 times rho. The rho factors cancel. 64 sevenths divided by 4 is 16 sevenths. Okay, let's move on. Problem 8 is also a centroid problem. But for now, let's bypass 8, since we did see an example involving a centroid. And let's look at problem 9, a mixture problem. So on this one, we're told that a container with 400 gallons of wine contains 20 gallons of alcohol. Wine with 8% alcohol is pumped into the container at a rate of 5 gallons per minute, and the mixture is pumped out at the same rate. Find the number of gallons of alcohol in the container after 1 hour. Okay, so I'll define A of t, the function A of t, to be the number of gallons of alcohol in the container after t minutes. So the number of gallons of alcohol So more specifically, it's the number of gallons of alcohol that's in the 400 gallons of wine. After t minutes. And we note, since we're starting out with 20 gallons of alcohol in the container, this initial value, A of 0, is equal to 20. So we'll end up using that fact a little bit later. Okay, in the second sentence, we're given a description of the rate of change of the alcohol in the container with respect to time measured in minutes. So the rate of change with respect to time is dA dt. Okay, so we have a certain amount of alcohol that's going into the tank, into the container, and simultaneously there's a certain amount of alcohol that's leaving the tank. So we're going to have a rate in minus a rate out. Okay, so if wine is being pumped into the container and it has 8% alcohol, then the amount of alcohol in 1 gallon of wine is 0.8. So I'm going to, in this first line, I'll put some detailed units in. So we're going to have 0.08 of a gallon of alcohol per 1 gallon of wine. So this is what it means to be 8% alcohol. And it's being pumped in, the wine is being pumped in at 5 gallons of wine per 1 minute. So the gallons of wine units cancel each other out, and so the units are just gallons of alcohol per minute. Okay, but then a certain amount of alcohol is leaving per minute. So some of the wine is being pumped out, and so we have capital A gallons of alcohol per 400 gallons of wine. And this is being pumped out at the same rate, 5 gallons of wine per minute. So the gallons of wine units cancel, so the output is also measured in gallons of alcohol per minute. Okay, so in the next line, we'll take out all of the units and just look at the numbers. So dA dt So 0.08 times 5 is 0.4. This measures gallons of alcohol per minute. And then minus A times 5 divided by 400. We can write that as 1/80th times A. Okay, so the goal is to solve this differential equation with the initial condition A of 0 equals 20. Well, this is a separable differential equation. So how do we separate it? Well, if we rewrite 0.4, that's 4/10 minus 1/80th A. A common denominator is 80, so we can write this as 32 over 80 minus 1 over 80 times A. And then factor 1/80th out. And when we factor 1/80th out, we're just left with 32 minus A. Okay, so now we have dA dt equals 1/80th times the quantity 32 minus A. So what we'll do is we'll divide both sides by 32 minus A and multiply both sides by dt. And we get dA over 32 minus A equals 1/80th times dt. And then we integrate both sides. We integrate the left-hand side with respect to A. And integrate the right-hand side with respect to T. Okay, so on the left-hand side, we get the negative of the natural log of the absolute value of 32 minus A. And on the right-hand side, we get 1/80th T plus a constant. And we'll go ahead and multiply both sides by -1. So we'll get the natural log of the absolute value of 32 minus A equals -1/80th T minus C. And then applying a property of logarithms, the argument, the absolute value of 32 minus A, is equal to e to the -1/80th T minus C. So using a property of exponents, we can rewrite this as e to the -C times e to the -1/80th T. Okay, when we remove the absolute values, so mathematically we should write 32 minus A equals positive or negative e to the -C times e to the -1/80th T. And the next step, we'll do a couple of things at once. We want to solve for A, so we'll add A to both sides and subtract positive or negative e to the -C times e to the -1/80th T. So when we do both of those at once, we get A equals 32 plus or minus e to the -C times e to the negative 1/80th t. Okay, well, the initial condition, a of 0 equals 20. So when t is 0, the value of a is 20. So when t is 0, we get e to the 0, which is 1. So that must mean that we need a negative 12 for a coefficient. You see how that works? So our function is for the amount of alcohol after t minutes is 32, a equals 32 minus 12 times e to the negative 1/80th t. To find the number of gallons of alcohol after 1 hour of this pumping, then 1 hour is 60 minutes. T is measured in 60 minutes. So just replace t with 60. So we get 32 minus 12 times e to the negative 60 over 80, or negative 3/4. And then you can use a high-powered calculator to find an actual number for that. On Friday's test, since calculators are not permitted, then this is the answer. This would be the answer. Okay, let's look at the differential equations in part 10 of the test review sheet. We won't do all 6 right away, but we'll start with part A. So this one, y prime equals x times e to the negative 2y with an initial condition y of 0 equals 0. So this is a separable differential equation. Okay, so for Friday's test, you'll just need to know 2 kinds of differential equations. First order separable, like this one, and then the other one, first order linear. We'll do an example of that a little bit later. Okay, so remember, y prime is shorthand for dy dx. And so now we separate the variable parts. So we're going to divide both sides by e to the negative 2y and multiply both sides by dx. If you divide by e to the negative 2y, that's equivalent to multiplying by e to the positive 2y. So the left-hand side becomes e to the 2y times dy, and the right-hand side will be x dx. Hey, it's okay to integrate directly, but I'll put in the intermediate step with the integral symbols. So the integral of e to the 2y dy equals the integral of x dx. And then in the next step, an antiderivative of e to the 2y with respect to y is 1/2 times e to the 2y. And on the right-hand side, an antiderivative of x is 1/2 x to the second. But we include the constant of integration on one side. So we want to solve for y, so we can multiply both sides by 2, and we'll get e to the 2y equals x squared plus 2 times c. Then take the natural log of both sides. The natural log of e to the 2y is 2y. And the natural log of x squared plus 2c is the natural log of x squared plus 2c. And then divide everything by 2. So we get y equals the natural log of x squared plus 2c all divided by 2. Okay, then the initial condition, y of 0 equals 0. That means that when x is 0, y is 0. So replace y with 0. And replace x with 0. So when will this be 0? Well, we know the natural log of 1 is 0. So when 2c is equal to 1. Okay, so our function is then y equals the natural log of x squared plus 1 all divided by 2. Let's do the next one. The next one is also separable. So I will start by replacing y prime with dy dx equals the natural log of x divided by y to the second. And then we separate the parts, so the left-hand side will become y to the second dy, and the right-hand side, the natural log of x dx. And then we integrate both sides, integrate the left-hand side with respect to y, integrate the right-hand side with respect to x. So on the left-hand side, we get y to the third over 3. And on the right-hand side, an antiderivative of the natural log of x. We've seen that a few times. This turns out to be x times the natural log of x minus x. And then we include the constant c. Okay, we want to solve for y. So first, multiply both sides by 3. We get y to the third equals 3x times the natural log of x minus 3x plus 3c. And then the cubed root of both sides. Y is the cubed root of 3x times the natural log of x minus 3x plus 3c. So 3c is just a constant. If you want to replace it with capital K, you can do that. Okay, the initial condition, y of 1 is equal to 6. So y of 1 equals 6. That means that when x is 1, y is 6. So replace y with 6, and replace every x with 1. So 3 times 1 times the natural log of 1 is just 3 times the natural log of 1 minus 3 times 1 and then plus. I don't need to do it, but I'm just going to put k instead of 3c. And we want to determine what the value of 3 is, or k is, I mean. The natural log of 1 is 0. So we get 6 equals the cubed root of -3 plus k. We know that the cubed root of 216 is equal to 6. Or you could raise both sides to the third power. 6 to the third is 216 equals -3 plus k. So the constant is 219. Okay, so our function is y equals the cubed root of 3x times the natural log of x minus 3x plus 219. Okay, that is our function. Okay, let's jump to part E. Okay, part E, we have not a separable differential equation, but we do have a first order linear. So the first thing we'll do is we'll divide both sides by 2x. And I'm going to replace y prime with dy dx. So divide every term on both sides by 2x, we get dy dx plus 1 over 2x times y. And when we divide 10 times the square root of x by 2x, 10 divided by 2 is 5. And the square root of x divided by x is 1 over the square root of x. And now we want to find the integrating factor. Our p of x is 1 over 2x. And so our integrating factor is e to the integral of 1 over 2x dx. So now we'll just focus on the exponent where the integral is. We can bring the factor 1/2 out front. And the integral of 1 over x. So we get e to the 1/2. The integral of 1 over x is the natural log of x. One half times the natural log of x. So in the exponent, we can rewrite that as the natural log of x to the 1/2. And so e to the natural log of x to the 1/2 simplifies to x to the 1/2, which is the same as the square root of x. Okay, so now we're going to multiply both sides of that equation by the integrating factor. Multiply both sides of that by the square root of x. So we get the square root of x times dy dx. And when we multiply the square root of x times 1 over 2x times y, I guess I can write it down in detail for now. The square root of x over 2x times y. And on the right-hand side, multiply 5 over the square root of x by the square root of x. We're just going to get 5. And then x divided by 2 times x is just 1 over 2 times the square root of x. So I'll rewrite the equation with that simplified. Okay, so the left-hand side is the derivative of a product of 2 functions of x. So I haven't done this yet, but just think of this as a derivative. So we want to find the integral of both sides, but let's leave it in the derivative form. The integral of this expression, square root of x times dy dx, plus 1 over 2 times the square root of xy dx. And then on the right-hand side, the integral of 5 dx. Okay, so the integral of this derivative is equal to the square root of x times y. And on the right-hand side, we get 5x plus c. Take the derivative of the square root of x times y. Then the derivative is the integrand of the integral above it. Okay, but anyway, we solve for y, divide both sides by the square root of x, so we get y equals 5 times the square root of x plus c divided by the square root of x. And then the initial condition, y of 1 equals 3. So when x is 1, y is 3. Okay, so in this equation, replace y with 3, replace x with 1, so we get 5 times 1 plus c divided by 1 is just c, so this means c is negative 2. Okay, so our function then is y equals 5 times the square root of x minus 2 over the square root of x. Okay, that's one example of this kind of differential equation, the first order linear. Let's go back to the hydrostatic force problem. So problem number 6. Okay, this one says a full swimming pool is 10 feet wide and 20 feet long. Its bottom is an inclined plane. The depth at the shallow end is 2 feet, and the depth at the deep end is 6 feet. Find the hydrostatic force on the bottom of the pool. Okay, so I'm going to attempt to draw the bottom, which is an inclined plane. The length of this side is 10 feet. And the shallow end is 2 feet deep, and the deep end is 6 feet. So the bottom of the swimming pool ranges from 2 to 6 feet in depth. So what we do is we break up the bottom of the swimming pool into rectangles, and we want to find the area of each of those rectangles. But our delta x is vertical, it's not inclined. So this vertical side of this right triangle is our delta x. And okay, the long side of the rectangle is 10 feet. And we want to know what the length of this inclined part of the rectangle is, because the area will be that number h times 10. Okay, so we're going to use similar triangles to help us. So this little triangle, I'll make a little bit bigger over here. So the vertical side is our delta x, and this side h is the side that we want. Okay, but the big rectangle, this rectangle, remember the horizontal side, the length of the swimming pool is 20 feet. And the shallow end starts at 2 feet and the deep end is 4 feet. So the length of this side is 4 feet. So this big right triangle, the 4 by 20, is similar to the smaller right triangle. And we can pare it down a little bit. If we divide both 4 and 20 by 4, and we get this rectangle with dimensions 1 and 5 for the 2 legs, then this triangle is still similar to that one. And the hypotenuse is the square root of 5 squared plus 1, or the square root of 26. Okay, so corresponding sides of similar triangles are proportional. So h divided by delta x is equal to the square root of 26 divided by 1, or just the square root of 26. And so h is the square root of 26 times delta x. Okay, so the hydrostatic force on this rectangle it's rho times g, and then the area of this rectangle is 10 times h, but h is the square root of 26 times delta x. So it's 10 times the square root of 26 times delta x, and then multiplied by the depth. So the x values start from 0, but we're only going to use the x values between 2 and 6. But we can still refer to the depth as x sub I or x sub I star. I'll just use x sub I for this one. Okay, so this represents the hydrostatic force on that rectangle. And we can do that on each of the rectangles in the subdivision. And so the hydrostatic force, when we take the limit of the Riemann sum, it's going to be the integral from x equals 2 to x equals 6. Rho times g in this setting is 62.5 cubic feet, or sorry, 62.5 pounds per cubic feet, multiplied by 10 times the square root of 26 x dx. Okay, so that's the integral to find the hydrostatic force on the bottom of the swimming pool. So this one's a fairly simple integral to evaluate. Okay, let's look at the other centroid problem. Okay, so this time we want to find the centroid of the region bounded by the graphs of two functions, y equals x squared and y equals x plus 6. Okay, so to find where the functions intersect, we set the functions equal to each other and solve for x. So x squared equals x plus 6, or x squared minus x minus 6 equals 0. This can be solved easily by factoring. The two factors are x plus 2 and x minus 3. So the graphs of those two functions intersect when x is negative 2 and x is 3. Okay, if you were to graph the two functions on the interval from negative 2 to 3, well, you would find that the graph of y equals x plus 6 is above the graph of y equals x squared on that interval. Okay, so let's find the moment of that region about the y-axis. So this will be rho times the definite integral from negative 2 to 3. And then we multiply x times the difference of the two functions. So x times the quantity x plus 6 minus x squared dx. So I'll leave most of the work for you to do. I'll just set this one up. So x times this quantity is x squared plus 6x minus x to the third. So that's a fairly simple integral to evaluate. Okay, then the moment of the system about the x-axis. Okay, this is where you have to be a little careful. We have rho times the definite integral from negative 2 to 3 of 1/2 times, and then we have to square x plus 6, and then from that we're squaring x squared and subtracting. So we'll take this a little bit further. Okay, when we square x plus 6, we get x squared plus 12x plus 36, and then minus x to the fourth. So it's sort of time consuming, but this is otherwise fairly simple to evaluate. And then the math is rho times the area. So it's rho times the definite integral from negative 2 to 3 of x plus 6 minus x squared dx. Okay, then by definition, the x-coordinate of the centroid is the moment of the system about the y-axis divided by m. And the y-coordinate of the centroid is the moment of the system about the x-axis divided by m. Okay, there's less than 2 minutes left, but that's enough time to say a couple of things about this differential equation, number 10, part D. This one is both separable and first order linear. So we don't have time to do it, but you can solve it treating it as a separable if you want, or as a first order linear. And so if you have time, it might be worthwhile solving it using both methods. But I still have a few seconds left. To treat it as a separable, first we add xy to both sides. And then on the right-hand side, factor x out. So we have x times y plus 1. And then when you do the separation, we get dy over y plus 1 equals x dx, and so on. Okay, we still have a few seconds if you want to try the first order linear approach. Okay, we're out of time now, but okay, so that's all. Go ahead and sign in for attendance. Tomorrow I will email the Zoom link for the test on Friday.